the periodic table had finally created order out of chaos. But it tells us nothing about why our world is as it is. Why some elements are energetic, others are slow, some inert, others volatile. It will be another 40 years before an entirely different branch of science came up with an answer. In 1909, Ernest Rutherford looked inside the atom for the first time. Rutherford proposed that the structure of the atom was like a miniature solar system, an overwhelmingly empty space with a few tiny electrons orbiting randomly around a dense, positively charged nucleus. But it wasn't until Niels Bohr came along, one-time goalkeeper for the Danish football squad and future Nobel Prize-winning physicist, that things really kicked off. He suggested that the electrons orbited around the nucleus in fixed shells, and it was his idea that was to lead to the discovery that these shells could only accommodate a set number of electrons. Imagine this football pitch is an atom, a single atom of an element. This is the nucleus. If this nucleus were to scale, my nearest orbiting electrons will be beyond the stands, so I've scaled it down. Here on the shell nearest to the nucleus, there can be just 2 electrons, then it's full. Here in the second shell, there can be 8 electrons, then it's fully occupied too. The third shell is happy with 18 electrons. And so it goes on. Outer shells can accommodate an increasing number of electrons. So electrons sit in discrete shells, never in between the shells. Bohr's theory would explain why elements behave as they do. It turns out that it's all to do with the number of electrons in the outermost shell. So, for example, Bohr's model showed that sodium has 11 electrons, 2 here, 8 here, and just 1 in its outer shell. And fluorine has 9, 2 here and 7 in its outer shell. To be completely stable, atoms like to have a full outer shell of electrons. So a sodium atom would like to lose an electron, to have a completely full outer shell. Whereas a fluorine atom has a gap in its outer shell, so by gaining an electron, it can complete it. In this way, a sodium atom and a fluorine atom can stick together by exchanging an electron, making sodium fluoride. Bohr's work, and that of many other scientists in the early part of the 20th century, led to an explanation of every element and every compound. Why some elements react together to make compounds, and why others didn't. Why the elements had the properties that they did. And this in turn explained why the periodic table had the shape that it did. Mendeleev had managed to reveal a universal pattern without understanding why it should be so. To find the answer, physicists had to delve into a subatomic world that Mendeleev didn't even know existed. This work was nothing short of a triumph. Even Albert Einstein was impressed. He wrote, "This is the highest form of musicality in the sphere of thought." But there was still one fundamental question left to answer. How many elements were there? Could there be an infinite number between hydrogen, with the lightest atomic weight, and uranium, the heaviest known element? In the early 20th century, a brilliant young English physicist, Henry Moseley, was determined to find out. He speculated that the secret lay within the nucleus, at the heart of each atom. Moseley developed a unique way of studying atoms, and scientists still use a similar technique today, although this X-ray spectrometer looks a bit different to the sort of kit that Moseley would have used. One of the elements that he studied was copper, and there's a small piece of copper inside here. Now, behind it is a radioactive source that fires high-energy radiation at the copper atoms. Moseley knew that the nucleus of the atom contains positively charged particles we call protons. He also knew that surrounding the nucleus are negatively charged electrons. Now, the radiation being fired at the copper is knocking out some of the electrons from the atoms. And this had the effect of making the atoms give off a burst of energy, an X-ray. And Moseley found a way of measuring it. He made a startling discovery. He found that copper atoms always give off the same amount of energy. On this graph, it's shown by this spike. And no matter how many times I repeat this experiment, I will always get the spike in the same position. It's unique to copper. Now, Moseley also experimented with other elements. And inside the sample, there are several others. So if I move it on to the next one, which is rubidium, and run this again, I get another spike in a different position. And if I move it on again to the next one, which is molybdenum, I see a third spike in a new position. Every element has its own energy signature. But his stroke of brilliance was to realize that this is related to the number of protons. He was the first person to measure the number of protons in the nucleus of an element, the atomic number. Atomic numbers are whole numbers, so unlike atomic weights, there can't be any awkward fractions. For example, chlorine has an atomic weight that comes in at an inconvenient half, 35.5, but a whole atomic number, 17. So Moseley realized that it's the atomic number, not the atomic weight, that determines the number and the order of the elements. And this is where it gets really clever. Because the atomic number goes up in whole numbers, there can be no extra elements between element number 1, hydrogen, and number 92, uranium. 92 elements is all there could be. There's just no more room. So Henry Moseley did the groundwork that enables us to say with absolute confidence that there are 92 elements, from hydrogen all the way to uranium. Moseley was just 26 when he completed his research, but his genius was lost tragically early. At the outbreak of World War I, he volunteered to fight, even though, as a scientist, he could have avoided joining up. He was killed in action, aged just 27, shot through the head by a sniper. A colleague wrote, "In view of what he might still have accomplished, his death may well have been the single most costly death of the war to mankind." The periodic table is a wonderful fusion of chemistry and physics. Mendeleev and the chemists worked from the outside with the chemical properties of each element, and the physicists worked from the inside with the invisible world of the atom, and yet both had arrived at the same point. The ordered design of the natural world had finally been explained in a pattern of pure intellectual beauty. So an era that had begun with scientists groping towards an understanding of the basic building blocks of our world had ended with that world entirely classified and made clear for all to see. And we never looked back. Next time, I'll follow in the footsteps of the chemists who labored to control the elements and combine them into billions of compounds that make up the modern world. I'll discover how modern-day alchemists are attempting to push at the wildest outposts of the periodic table to create brand new elements. And I'll find out how the power of the elements was harnessed to release almost unimaginable forces.